started in class. We did those first few slides, but I just wanted to take a second and give you guys props because we're getting into new ratios today, right? New ratios today. We already talked about the tangent before you guys left break, and the tangent has limitations. So if you saw in the first do now, it was more work with the tangent to get what this hypotenuse was. It was possible, but we got there to get the hypotenuse. It's because we knew what the opposite side was. If you know what the 64 degrees is here, then tangent of 64 degrees is an equal opposite over adjacent. So you can solve for the adjacent. And once you have both the opposite and adjacent, you can get the hypotenuse by using the Pythagorean theorem. A squared plus B squared equals C squared. So that's what we did on do now number 1. Do now number 2, hopefully this didn't overwhelm you. It shouldn't have overwhelmed you, or really it should have, right? First of all here. And the moral of the story here with do now number 2 is that the tangent was not enough. That's right, wasn't enough here. There's no way really for you to solve this one without learning some more math, without learning some more skills, without learning some more things. And that's why we're just jumping into it this Monday by learning some new stuff here. Okay, so tangent of 35 degrees, we know it's y over opposite over adjacent, right? Opposite side over adjacent side here, but we don't know either of the sides there. Right? We don't know either of the sides there. So sure, we could look up what tangent of 35 degrees is here to figure out what the ratio is between those and see, maybe we can do some fancy work here with the Pythagorean theorem and figure it out somehow, but it's just too much work here, right? Tangent of 35 degrees is that 0.7. So this would be in a 0.7 to 1 ratio. And, I don't really want to go there. Okay. So anyways, tangent's not enough here because we don't know either the opposite side or the adjacent side. So maybe there's another way, okay? Maybe there's another way to get this opposite side if we know the hypotenuse, okay? If we know the hypotenuse here, okay? So if we know an angle in a right triangle and a side, is that enough to get one of the other sides here? That's sort of one of the things we're going to think about here as we jump into what today's lesson is, which is going to be more ratios, okay? Beyond the tangent ratio, there might be some other ratios here that could help us and help getting us through this here. So today we'll return to similar right triangles to understand where some new trigonometric ratios come from and why they work. Then you're going to begin using 2 new trig ratios to solve problems here, okay? So anyways, hopefully you started this with your group. Hopefully you've done this here. I'm just going to kind of do these slides with you guys here because I know it's a Monday. You're getting your bearings here and figuring out where you are, right? You're at home still after over spring break, but now you got some responsibilities, right? Your life as a student is continuing now. So anyways, I'm hopefully going to walk you through this a bit here. So check this one out here. We got this first question. If angle D is the reference angle here, drag the labels to show which of the hypotenuse, which is adjacent, which is opposite here. So I'm going to go ahead and do that for you guys. I'm just going to do the whole lesson with you guys today. So you can pick and choose what you want to watch here. But anyways, just double check here. This should be pretty quick at this point here. That's the reference angle right here. Angle D is 35 degrees. That's its opposite side. This is the adjacent side. So again, find the legs. And then whatever leg isn't part of that actual angle there, well, that's got to be the opposite side. And then whatever leg is part of the 35 degree angle, right? Here, the 35 degree angle has this ray and this ray. There's our adjacent side and there's the hypotenuse here. Anyways, we've used the tangent ratio opposite over adjacent to solve for the lengths of the legs. What other ratios might be useful? Well, in the do now number 2, right? If we happen to know, right, we knew opposite of ratio, but if we knew, for instance, if we had a ratio that was, this is where I can get like kind of a fraction symbol down there, which I want in a second because ratios are ultimately fractions. Well, what if I knew what the ratio would be between this length y here and this 10 centimeters? What if I knew the actual ratio of this side over that side? Would that have helped me solve this problem? Yeah, it totally would have here. So if I knew what the opposite to hypotenuse ratio is in a particular right triangle with a particular reference angle, that could have helped me solve that problem, okay? So reminders on right triangles with a particular angle measurement is that it's gonna be similar to any other right triangle with that angle measurement here. So triangle DEF has a hypotenuse of 10 centimeters, and a reference angle of 35 degrees here. But you know what? It'd be similar to another triangle with a 35 degree reference angle and had a hypotenuse of 20 centimeters or 15 centimeters or 16 centimeters. Why is that important? Well, the opposite to hypotenuse ratio should be the same with all of those right triangles here. And do you think mathematicians have helped figure us out what the opposite over hypotenuse ratio is for a 35 degree reference angle? Well, yes, they have. We'll get to that later in the lesson here, okay? So that's why that would have been the one that was helpful for our actual do now. But another one we're going to talk about today is going to be the opposite over hypotenuse. We'll definitely talk about that. Well, why don't we talk about the adjacent to hypotenuse ratio, okay? Or the hypotenuse to adjacent ratio, or a hypotenuse to opposite ratio. So anyways, the ones we're going to deal with here are going to have hypotenuse in the denominator, okay? So you might be saying you might have written hypotenuse over opposite here. I think that's a good answer. Or hypotenuse over adjacent. I think that's a good answer too. But the thing that we're going to care about here is hypotenuse in the denominator, okay? The ratios we're going to study this year in geometry are going to have the hypotenuse in the denominator here. When we need to use the hypotenuse to solve a problem, or if we're solving the hypotenuse, that'll always be going to be the denominator of your particular trigonometric ratios here. Okay, if we knew the adjacent leg length, or we're trying to solve for the adjacent leg length, we have the hypotenuse. We might care about the adjacent over hypotenuse ratio. Does that have a name? Well, we know that opposite over adjacent, that's the tangent ratio. These are going to have names a little bit later. Opposite over hypotenuse and adjacent over hypotenuse. Hopefully I haven't bored you to death yet. That's why I did my fancy dance at the beginning here. All right, gather data on some side lengths for right triangles with a 35-degree reference angle. This right triangle is 35-degree reference angle. There we go. And look, they actually have the side lengths here, right? They have the side lengths here of this freaking right triangle with a 35-degree angle. Remember, it's similar to all other right triangles that have a 35-degree reference angle. And so these ratios are going to be true for any right triangle with a 35-degree reference angle. It's crazy. Anything. All right, so this right triangle is a 35-degree reference angle. Record the lengths of the three sides in the table below. Adjust the red dot to change the size of the triangle. The angle's going to stay 35 degrees. Record the new set of measurements for that triangle. Repeat until you've recorded the side lengths for three different triangles. All right, anyways, let's just let this be triangle number one, the default one that's given to you. I assume it's the same one given to you as was given to me. So let's write the measurements down. Hypotenuse here, okay? Maybe you did this with your group already. Maybe we're doing go, Mr. Fortin. That's fine. Let's just do it together here. Hypotenuse here is 2.742. Opposite is 1.573. And adjacent is 2.246. Okay? And here, let's create some similar right triangles here. So I could make this smaller. Look at that. Smaller here, but it's similar to the one that I just looked at a second ago because it has a 35-degree reference angle and it also has a 90-degree right angle. So the original triangle that we had at the beginning, 7 point, what was it? This was this here, 7 point. I can't even do it anymore. Precisely. But anyways, something like this is similar to something smaller because of AA, right? If AA, a 35-degree angle and 90-degree right angle. Those are the two constants here that we can tell in this diagram, but you know what? They're similar to each other by A, so they have that proportionality of the side lengths here. So my opposite over hypotenuse ratio should be the same. That's what you're going to look at today. My adjacent over hypotenuse ratio should be the same. That's what we'll look at today. So let's let this be my second triangle. So let's check this one out here. I'm 2.18 for the hypotenuse. Opposite, hitting tab. I think that's the problem here. Opposite's going to be 1.25. Yeah, the tools are kind of janky. Tools aren't super fun to type in and stuff like that, but it's kind of neat, right, that you have that constant ratio here that we're going to look at in a second, that there's similar triangles here. And we're just going to observe this here. So let's make a big one. We'll make a big one. Really make this very dramatic. Well, I got to see what it is. All right, 2.06 for my opposite side. I'll move Mr. Fortin out of the way here. 2.06. Adjacent side, 2.949. Hypotenuse is 3.6. There we go. Okay, so I think, I'm guessing, I actually haven't done this one yet, but I'm guessing where this assignment's going, it's a cool little neat Dismal task, is that let's look at the ratios now. Let's check it out here. Let's see what we notice here. Oh, yeah, we have to actually calculate it. I have to calculate it here. Use the Desmos calculator, calculate each ratio, and what are we expecting? What are you predicting? Well, what have we been talking about last slide? All these triangles are similar to each other by AA, so they have this interesting idea of proportionality. Let's just verify that it's true here. Okay, opposite to hypotenuse ratio here is 1.5573 divided by, we're not doing tangent, right? So we're not doing opposite of adjacent, not doing opposite of adjacent, not doing opposite of adjacent, although that would be the tangent of 35 degrees. We can verify that in the calculator. We're doing opposite to hypotenuse here, so 2.742. What do I get? I get 0.5736. 0.573. What does it say? 3 decimal places? Okay, there we go. So I'll round up to 4, 0.574. Okay, let's keep going here. So I'm going to get the opposite hypotenuse of the 3 triangles here. So the second triangle was, that was my small one. See, my opposite side is smaller than 1.5 here. Anyways, opposite to hypotenuse. I can hit enter here to get to a new row. All right, little trick here, little trick. Desmos tricks, really good. There we go, 1.25 divided by 2.18. And, ooh, that's pretty freaking close. That's pretty freaking close. They would be identical, but, we had to round this, right? We had to round this. This was rounded 2 decimal places, most of them. Sometimes we got 3. I guess they gave to us a 3. But anyways, they're almost identical. Should they be identical? Well, yeah, if we could keep not round, or if we didn't round at all earlier, these should be identical. Because remember, they're similar triangles. So our opposite hypotenuse ratio is going to be the same too, right? So it's similar to what we've already talked about. We've spent the last couple weeks proving beforehand, talking through is like, these similar triangles get us to consistent ratios that are going to become very important in future math classes to take care. All right, this is going to round up. Ooh, this one actually doesn't. This one rounds down here. We're going to 3 decimal places. So it's not exact, but again, rounding errors, right? Rounding errors, I think, got us there. So anyways, last one, let's check it out. What are we predicting? Well, 0.573 or 0.574. And let's just make sure that that is what it is. There we go, 0.572. So anyway, that was a big triangle. They're almost exactly the same. They should have been exactly the same here. All right, opposite. There's my opposite over a hypotenuse ratio. We'll get a name for that later. What about adjacent over hypotenuse here? And we'll, these are kind of related. Maybe we'll talk about a bit, kind of how they're related a little bit later. Perhaps it'll come up. But let's check it out here. 2.246 divided by, not doing adjacent over hypotenuse. That would be the inverse of the tangent. We're not doing that here. We're doing adjacent hypotenuse, okay? Adjacent to hypotenuse ratio, right? Hypotenuse is always in our denominator here. That's going to be a key thing that you can count on for the rest of this chapter, right? The rest of this year that we have here. It's always hypotenuse will be in the denominator, right? When we are ratios. So 2.246 for the adjacent side of triangle 1, and then 2.742. Okay, so I have an adjacent over hypotenuse ratio for this triangle of 0.819. Okay, next up, I got this. I got 1.786 divided by 2.18, and there we go, 0.189. How about that? 0.189. 819. What am I talking about here? It's exactly the same, the 3 digits here. Again, rounded, so our numbers are like slightly off as we go beyond the 3 digits here, but pretty much freaking the same thing. And this should be the same thing, right? Because they're similar triangles, right? I had my medium size, my small guy, and then what about my big guy, right? Let's see if I can get 0.819 for my adjacent hypotenuse ratio for this particular triangle, which is similar to the other ones. Should be proportional, right? So it should have the same ratio. And we'll get this to be 2.949 divided by 3.6. Oh, I wrote that wrong. It's 2.949. There we have it, 0.819. Perfect. All right, so what do we notice here? Hey, our ratios are also consistent as we compare the legs, either leg, to the hypotenuse. Opposite over hypotenuse, adjacent over hypotenuse for a particular reference angle will be the same, right? Will be the same here, and we'll get the names of these ratios coming up a little bit later. What do you notice about the ratios? They are the same for any 35-degree reference angle. Hey, doesn't matter, right? Doesn't matter how large the right triangle is. Our over hypotenuse and adjacent over hypotenuse ratios will be the same. All right, we had medium triangle, small triangle, large triangle, and we had the same opposite over hypotenuse ratios for all 3 of them. Same adjacent over hypotenuse ratios for all 3 of them because we had the same 35-degree reference angle. So all of those triangles were similar, consistent ratios, right? And we'll get names for these because this is important here. Class averages, I'm the only one who's done this so far because I'm filming this one over spring break, getting ready for it. But anyways, this will check their answers against the rest of the class, aggregate it, and is this the same as what you got? Well, it does. I'm the only one who's done this so far. I'm hoping if you did it correctly, you probably got what the class got, or else the class was just way off, I guess. But anyways, explain why the results are similar. Well, we are all using a 35-degree reference angle. So all triangles the class looked at are similar by AA. Therefore, I'll say before therefore, I'll just say since similar triangles side lengths are proportional by definition of similarity, right? That got us to it. Defines how similarity gets set up here. By definition of similarity, then the opposite over hypotenuse and ratios will all be the same by definition of proportion, right? Because the proportions are equal ratios, right? Equal ratios by definition of proportionality. Definition of proportional. I like that better. Okay, then the adjacent over hypotenuse ratios will all equal each other by the same reason. There you go. I don't know if you see my answers when I share the class, but anyways, there to appear here, and hopefully you get to see other people's reasoning down there to sort of justify this here. Okay, I'm going to keep moving on here, right? Well, I'll definitely look at that slide to see if you put stuff down, right? You got to look at other people's here and refine that thing. So when I'm grading those, I'll definitely look at that slide here. This is good here. I like doing these assignments because I know what to look for when I'm looking forward to see how you guys did on the stuff here. Why trigonometry works. Hooray, trigonometry. So you've got to be almost there, right? The stuff we're going to study this year is just these three ratios. The opposite over adjacent ratio, which is called the tangent ratio. Okay, opposite over adjacent, tangent. Tangent, opposite over adjacent. Tangent, opposite over adjacent. Toe up, because T stands for tangent. O is opposite, and A, right? Adjacent. Okay, TOA. We're going to have a couple new ones, right? Two more ratios here for trigonometry. That's all we got to worry about this year. How we solve problems with them. We have opposite over hypotenuse. What's that ratio called? We're going to have adjacent over hypotenuse. What's that ratio called here? So anyways, it's no coincidence that our class ratios for the 35-degree reference angle were all similar. Hopefully they're all the same because the triangles are similar. Drag the red point to verify the opposite hypotenuse ratio has about the same value for any sized right triangle with a reference angle of 35 degrees. There may be slight differences due to the rounding side lengths. What does it say? Drag the red point. Oh, is it going to show me? Yeah. All right, cool. Oh, that's pretty good, sweet. That's awesome. I love that. Oh, this is great. What a great assignment this is. You're like, what? It's Monday after spring break. This is a great assignment. Come on, agree with me. Please agree with me. All right. That's pretty neat. And, I think rounding errors, it sometimes goes down to that 0.573. But anyways, yeah, similar. Okay, I'm not going to write this in. I just said in the last slide. But you say something about similar in your explanation here. I think you study similarity enough and tangent ratio enough here where you guys can come with an answer this year. I don't need to explain it here. But that's pretty cool, okay? Right? Corresponding side lengths of similar triangles are proportional. Gonna have the same ratio, opposite of hypotenuse. That ratio here, right? This to that, okay? It's just division, right? You end up with a decimal like this, okay? And that's the thing we're gonna care about. That's gonna be stored for us in our trig table and our calculators here, okay? New ratios here. Previously, you worked with opposite over adjacent ratio and learned that's called the freaking tangent ratio. You got that one here. Now you have two more ratios you can work with to solve problems about right triangles. The sine ratio and the cosine ratio. Sine and cosine. So on your calculator here, hey, this is a big moment. Stay with me. I know you're probably zoning out here, right? I'm trying my best to make these things interesting, but who knows? All right, sine and cosine, they're on the calculator, on the freaking calculator. Check it out here. We got cosine here. I can actually make some, I'm going to make some, come on. Yeah, mouse is what I want here. I'm gonna make some fireworks here. Check it out here. Sine, boom, right there. Cosine, boom, right there. Check it out. I'll clear it out here. So tangent, boom. Okay, so you're learning 3 major buttons on a calculator, on a scientific calculator: sine, cosine, and tangent. Hooray, right? We hit them. I'm just going to tell them to do stuff. We're not going to do more than one thing at once. But anyways, cosine, that's K-O-C-O-S here. Stands for cosine. Sine, right? S-I-N, not sin. Don't call it sin. If I already told you called sin, I think we'd be talking about another geometry teacher, not the sine function. S-I-N-E stands for sine, and that's opposite over hypotenuse. Sine. So, sine. Sine is opposite over hypotenuse. So, S-O-H. You're like, this guy's making no sense. So, what is he saying? So, it'll all make sense later. Trust me, there's a saying. It's classic, right? We've been going on my whole life. Well, before that, people keep these 3 ratios stuck in their heads correctly. And TOA, we've talked about that. Tangent is opposite over adjacent. So is sine equals the sine of a particular reference angle, right? Particular angle. Sine of 35 degrees. Oh, we got a celebration there with the fireworks. Sine of 35 degrees is its opposite over hypotenuse ratio. So, S-O-H. S-O-H. So, that's what you remember. So anyways, there you have it there. Look at that, opposite over hypotenuse. Sine ratio, the ratio between the length of the opposite side and the length of the hypotenuse side. The cosine ratio, okay? Sine is this over that. Cosine is going to be this, that over this, right? Or this over that. Sorry, this over that, and then again, this over that, right? Different thing here. Cosine ratio is the ratio between the length of the adjacent side and the length of the hypotenuse side. There it is. Like, blow it up right there. Cosine is adjacent over hypotenuse, or ka. Cosine, adjacent, hypotenuse. C, cosine. A, adjacent. H, hypotenuse, okay? You have to know what these ratios are. You have to memorize this, okay? So that's why I say ka. Cosine equals adjacent over hypotenuse. Cosine, a particular reference angle, right? Because we're talking about, that's what establishes that particular ratio here, okay? So anyways, that's it. So I've told you the ones so far: TOA, so, and ka. But what we call this, to keep things in mind here, is a big moment. And the first time I'm going to tell you this, if you're watching the video, big moment, the way we all memorize this. I'm Mr. Fortin memorized this year. All the other math teachers memorized it when they grew up, and they did this too. You're memorized it. At college parties, you'll ask people what trigonometry, what that's all about. And the first thing they're going to say is this. Wait for it. SOHCAHTOA. 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 So, sine of a particular reference angle equals its opposite over hypotenuse ratio. Cosine of a particular reference angle equals the adjacent side length over the hypotenuse side length. And then TOA equals the opposite side length over the adjacent side length here. SOHCAHTOA. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. What are we doing in class today? Well, we're using SOHCAHTOA. That's what we're doing over the next week plus until we get to our quiz, which will be next Friday. Oh, yes, here. These ratios will have the same values for any similar right triangle with the same reference angle. So that's why we say that these are, right, the sine, cosine, and tangent ratios of a 35-degree angle, right? Its tangent ratio would be this over that, okay? It's over the reference of a 35-degree angle. Its sine would be this over that, and its cosine would be this over that, okay? So anyways, going to be the same for any reference angle. And boom, there we go. We have it here. Check it out here. Table of trigonometric ratios. So I know your calculator can do a lot of this. Desmos has this hanging out right here. Check it out here, but you got to know how to use these ones too. This is on page 271. Okay, 271. You probably wondered about this. Like, what the heck these things were all about here? Oh, I'm looking at Algebra 1. I didn't mean to do this. Oh, wait. I actually can't do this. I'm just looking at, I can't actually switch to a different view. But anyways, page 271, you have the trig table there. Here, sine, cosine, tangent, it's just a different trig table for you here. But in the olden days, you would just use these trig tables. Now you can use your actual calculator. Okay, so no calculators, no Desmos. Mathematicians worked out the ratios by hand, and then they put it in, right? By hand, they figured it out. They figured it out for us. They put it in here, a table. So on page 271, your textbook, you can use that to figure out the sine ratios, cosine ratios, and tangent ratios of a particular reference angle. But the more important thing for you in the future isn't page 271, because you won't have that trig table with you. When you take that in standardized test, you got to use the calculator. Okay, got to know how to use this here. So it says here, use the Desmos calculator to find sine of 35 degrees. Boom, should be easy enough. Sine of 35. 0.573 or 0.5574. Look at that. It's like 0.5735, and when it's 5, you round up, right? 5.7 especially. That's closer to 3.54 than it's 0.574, right, rather than 0.573. So we were right about that. The class average was right, which was just me, of course. So anyways, let's do it here. 0.574, okay? And anyways, how does it compare to the table here, sine of 35 degrees? Well, they don't actually show us. We can't even see it here. How the values compare to the ones you found? What is that talking about? Where are the values I found? The calculators are the values I found. It's longer. It's more precise. Okay. I'm going around. I'm going to do the whole thing here. 5.764, 3.64. All right, it's fine to get the freaking cosine here. Do the next one here. Cosine 35 degrees. Okay, 0.81, 0.819, 152, 0.443. Okay, compared to the values I found, the calculated values I found are more precise, or digits, right? We get more digits of it than a freaking table, right? A trigonometry table here. So trigonometry table, obviously, to save space, they don't show all these digits here. It's a little bit less precise, okay? It's more rounded, okay? So anyways, you get to see some of your classmates' answers, which is kind of nice here too. Now you have the tools to solve this problem. Hey, let's do it, okay? So let's wrap it up. These last few slides here are going to be us solving trig problems with one another. So I might break this into a separate video so that we can kind of look at it a little differently here, depending upon what you want to watch. But anyways, solve for the side length y using the triangle tools you've been learning about. Solve your work in the text box and on the sketch. Start by labeling the sides opposite, adjacent, or hypotenuse. Think about which trig ratio you can use to solve. All right, so we're going nice and slow here. Let's get this. So this was the do now, number 2, the one you couldn't get. And I told you at the beginning of class, you're going to get this one. There's an easy way to do it. So just watch the video, like work with the groups. Hopefully you get this here. I know, I wish we had more time to do this stuff in our groups. It's kind of too bad here. All right, so anyways, let's do it here. Well, I got to figure out what my opposite side is. And I don't know what my adjacent side is, but I know what my hypotenuse is. So what I want to do is I want to use the, not tangent ratio. Tangent would be opposite over adjacent. I want to use opposite over hypotenuse. So I want to use so. I want to use so here. I want to use sine. Okay, I want to use sine here. So sine of a 35-degree reference angle, and I can just show all the work down here so you can see how I would do this if I were doing this by hand on in my notebooks here, which I'd recommend you do so you have this as an example. It would just be y over 10 centimeters, okay? Opposite over hypotenuse is the sine ratio. Get used to it. You're going to be using that a lot here. Okay, so to solve for y, I'd simply have to get rid of this dividing by 10 centimeters. I'm going to figure out what sine of 35 degrees is. I'll do that a little bit later. What I'm going to do is I'm going to multiply both sides by 10 centimeters so that I can isolate y. So here, I'll do this over here. Multiplication property of equality. Multiply this by 10 centimeters. And then I'll multiply this by 10 centimeters. Ugh, messy, okay? And now I'm going to do 10 centimeters here times by sine of 35 equals y. And I have y isolated because, 10 centimeters divided by 10 centimeters, those are inverse operations. They cancel each other out here. And so now I have 10 centimeters. Oh, it's messy. Decimalist writing is messy here. Remember that? And I'm going to do 10 centimeters times by sine of 35 degrees, and I'm going to be good to go, okay? So I'm going to do 10. You can even just type in this whole statement you have here, right? 10 centimeters times by sine of 35 degrees, and that's going to tell me my answer. And what do I get? I got 5.73, and that makes sense. I think that makes sense here. This looks like it's about half as long as this, maybe a little bit longer than half the length of that hypotenuse. Hooray, we got what we wanted here. So 5.73, round up to 4. Do that 4 decimal places, or 3 decimal places like they did earlier. Answers in centimeters too, okay? Because we knew our hypotenuse was in centimeters. So that leg here is going to be in centimeters because it's going to be in that whatever 0.574. Yeah, 0.57. Look at it, 0.574 to 1 ratio of opposite over hypotenuse that we've already seen so far. Okay, got to put our answer down here. So y is about says rounded to the nearest tenth. Okay, so let's do it here. We get to share with class as well. So I'm gonna do about 5.7. Yeah, and that's the nearest centimeter there. Okay, nearest tenth. Share with class. Okay, hopefully you get to see your answers. That's kind of nice here that you can see what other people had here. Okay, another problem that you have here. So it looks like you have another problem to solve. So let's go ahead and do this one here. Solve for the missing side lengths using the triangle tools you've been learning about. Show in length text box and the sketch. Okay, I'll just do it, I think, in the text box here, because maybe you can see what I'm doing a little bit more clearly. Okay, label the side lengths here. I think that's pretty important. Okay, so I'm not going to care about tangent on this one. Well, actually, I might. Maybe later I'll use tangent if I have this here. But so let's just label all sides here. I got my opposite side. I have my adjacent side. Okay, because I have this 24 degrees. That's going to be my theta. That's going to be my reference angle. And then this is going to be my hypotenuse. Okay, right here. So I might as well just use sine again to get x. And then we'll figure out what we need to do to get y after that here. But this is going to involve, I think, maybe just using two trig ratios here. So what I'm going to do is I'm going to do sine first, okay, because that's right? Opposite over hypotenuse here. So I'm going to use the sine, and again, it just looks like sin here. But again, if you say sin, I'll think you'll be talking about another geometry teacher at Lowell. So if you say sin, okay, right? Ever heard of Mr. Sin? I'm talking about an actual person whose last name is Sin. Anyways, here, sine of 24 degrees equals x over 14. I might just do this quickly in my calculator, okay? Because what I have to do to both sides, well, I have to multiply both sides by 14 to get rid of that, right? Opposite over hypotenuse there, okay? So I'll multiply both sides by the hypotenuse to bring the hypotenuse over here, and the hypotenuse times whatever that ratio is what's going to give me my opposite side. And simple as that, okay? So I'm going to go ahead and do this. 14 times by sine of 24 degrees, and I got about 5.7. So it's to the nearest tenth, so I'm going to go with that, about 5.7. Okay, there we go, 5.7. Okay, so I got to see your work here. You can't just be watching this video and just putting in the answers. So I will be checking that out here, that you showed your work here. And you know what? I'm not going to put the answer in. I'm not going to put the answer in for y, because you should be able to get y by now, right? Like if this were the opposite side and we know it's 5.7, okay, there are a couple ways I could get y here, right? I could use Pythagorean theorem to get y. Sure, again, this is 5.7. So 5.7 squared plus y squared would equal 14 squared. But what might actually be faster is by using the cosine, right? Using the cosine here, right? Cosine, so ka, toa. SOHCAHTOA. College parties, right? They say, what do you remember about trigonometry in high school? SOHCAHTOA. Heck yeah, SOHCAHTOA. Like, yeah, we learned that in our school too. Anyways, cosine of 24 degrees equals, right, adjacent over hypotenuse, okay? So equals y over 14, okay? You have one unknown there because you know what? Our graphing calculator, or just any calculator, any scientific calculator, is going to know what unique ratio, right? Adjacent over hypotenuse ratio for a 24 degree reference angle has to be. There you go there. I'm not going to put the answer in here. I just want you watching this video, just getting the answers and putting them in here. Do some of the work as well, too. Yeah, I know you guys do a lot of the work here. Almost everybody does this here. All right, check this one out here, right? Another one here, 3B. I thought we did 3B. We did 3A? And we did 2. Oh, okay, I see here. So yeah, all of a sudden they're just doing A, B, and C or something like this here. All right, solve for the missing side lengths here using triangle tools. Learn about here. All right, label it up. Okay, when I do this one, I label them up right away. So here, I'm used to doing tangents, so I'm used to labeling my opposite and adjacent sides. Okay, I also have my hypotenuse. Okay, I got my hypotenuse here. And that's going to be the key to figuring out which of these tangent ratios, not tangent, which of these trig ratios here. So we're beyond tangent, man. We're beyond tangent because we have our hypotenuse given. We don't have our adjacent or our opposite sides. So we're not going to use tangent because we're going to use one of the ratios that involves the hypotenuse here, cosine or sine, okay? Start with sine, I guess, right? Sine is fewer letters than cosine, right? What does the co stand for? Ooh, we'll think about that maybe next lesson here. Okay, so I'm going to do opposite over hypotenuse here, so I'm going to do sine. So sine, okay, maybe put an example or two in your notes. Can't hurt to do that. Sine of 76 degrees equals b over 21. Okay, opposite over hypotenuse, opposite over hypotenuse, opposite over hypotenuse. Oh, so, sine, so. All right, sine of 76 degrees. So let's just do it. I'm going to do it out here. It's not too hard, right? 21, I'd have to multiply both sides by 21, right, to isolate b here. So I'm just going to do this. I'm going to do this kind of quickly rather than show all the workout this time, because I showed on the last slides here. So I'm looking for more work. Please rewatch the last section here. Sine of 76 degrees. I'm in degree mode. Very nice here. So 20.4. That's what I got for B. Okay, so I got 20.4 for B. What do I going to get for A? Okay, well, I'm just going to use cosine for this. I'm not going to type this in here, guys. I just talked through it. Okay, so B equals 20.4. Fine, I'll type it in. Fine. 20.4. What about A? Cosine of 76 degrees. Okay, that's going to be the adjacent over hypotenuse. Okay, so that's going to be A over 21. And same deal, right? I have to type that one in, right? Just 21 times cosine of 76 degrees. Boom, you're good to go. You got a rough, the squiggly lines here. It says approximately to nearest 1/10, whatever that is here. Okay, let's multiply through. I don't need to do the rest for you guys. You got this. Practice. Hopefully you're feeling a little more confident now. It's not just tangent ratio anymore. We got sine and cosine. And hopefully you justified it. Hopefully you're pretty good about justifying it by you talking about similar triangles, right? Similar triangles and how that the adjacent to hypotenuse ratio has got to be the same for any reference angle. The opposite of our hypotenuse ratio got to be the same for any reference angle. So hopefully you feel okay about the whole proof component of it, even though we didn't write a two-column proof. Hopefully you see it. Hopefully you understand it. All right. Anyways, next one here. Man, easy enough. I don't think you needed more trick questions. Trick questions were all at the beginning to help you realize that tangent is not good enough. Not good enough in a lot of situations here. Okay, so this one here, okay, this is my opposite. Oh, this is tough here. I got two reference angles here. Okay, let's have this. This is going to be my theta right here. That's going to be my reference angle. Okay, let's not bother with the 73 degrees. Let's not. I mean, maybe bother with it later, but I'm not going to bother with it now. Okay, so I'm going to do. Oh, and then this is my adjacent. This is my adjacent side, so I know that. So I'm going to use the tangent on this one. Yeah, so this is kind of like a trick question here. And this is my hypotenuse here. Okay, I don't know my hypotenuse. I don't know my hypotenuse. So you know what I can do is I can do cosine. What's it? Make the pieces come together. Make it sort of work for you here. Cosine is adjacent over hypotenuse. Do I know the hypotenuse? No, but I know the adjacent. Right? I know the adjacent here. So cosine of 17 degrees. Okay, that's going to equal. Okay, I know the adjacent. That's 19. Okay, but I don't know the hypotenuse, and that's n, right? That's n right here, okay? So remember, when you're solving a problem like this here, you can multiply both sides by n and divide by cosine of 17 degrees. You can do that. That's one way to do it. You could cross-multiply, right? That's one thing you do. You can make this cosine of 70 degrees over 1 and then multiply it to 19 and then times this. Anyways, but you could also do an extreme swap. That's the thing that I do when I do problems like this here. So I'll make this cosine of 70 degrees, whatever that decimal is here. I'll put that over 1, right? A decimal over 1 just equals whatever the decimal is, because dividing by 1 just makes it the same thing. And you know what? I'm going to, instead of swapping my means here, I'm going to swap my extremes. You can extreme swap. You can do that. So n equals 19 over cosine of 17 degrees, and that's all it's going to take. Ugh, messy. So hopefully you're listening to me so you realize what I wrote cosine of 17 in the denominator there. So I'm going to go ahead and do 19, and I'm going to divide by cosine of 17 degrees, and I got approximately 19.86. Does my answer make sense? Yeah, the hypotenuse is longer than that leg. It's a long leg too, so not much longer, but it is longer. So I got 19.9. And then opposite side, I'll let you guys do that here. Video's been long enough here. Opposite side, you can use Pythagorean theorem to get that. You could. M squared plus 19 squared equals approximately 19.9 squared. Okay, you can do that. Or you could also do another trig ratio. Get practice using that, right? Yeah, do it. That's just TOA, right? TOA. Yeah, you can just TOA. Yeah, you can do it. You can use the TOA thing. Okay, tangent is opposite over adjacent, so you can do that. That's super easy. Okay, tangent of 17 degrees equals opposite is m over adjacent is 19, and that's that, right? That's an easy one. That's a super easy one. So you just do 19 times tangent of 17, boom, gives you what the m is. That's a lot easier than the Pythagorean theorem. All right, hopefully you guys watch this and realize this isn't too crazy. Summarize your learning right here. Okay, why did trig ratio work? Can you actually explain that to yourself, to a friend? Okay, if you want to talk about similar triangles in that one, do it. Okay, what are the steps to solve problems involving right triangles? Okay, right, label, right? I'd say label like the freaking sides. Find a reference angle. Label opposite, adjacent, hypotenuse. Okay, then use a trig ratio. Okay, for that reference angle. You're gonna have to use your calculator. Okay, so word it out. So this will help you if you're using your words here. Remember what to do when you solve problems later. Be more confident, at least here. How can you remember the 3 trigonometric ratios? Yeah, I would love it if I could see this. SOHCAHTOA. SOHCAHTOA. There it is. So I'm looking for you. Props. You're totally geometrically awakened. Your second semester geometrically awakens if I see SOHCAHTOA there as the number 3 in your reflection. Okay, so hopefully you watch this video. Hopefully you got that. If not, you're going to hear lots of SOHCAHTOA coming out later. All right, how long was this video? Oh, man, 40 minutes again. Happy Monday. Welcome back. Take care.